So good evening, all of you. So this will be the seventh video, seventh live session on problem solving approaches of the topic structure, stereochemistry, and reactivity of organic intermediate. So in this video, we'll look towards the problem on the week 7 content, which uh, taught by Professor Amit Basak on in the 7th week. Right. So I will take first problem one by one, and then at the end of session, I will discuss the doubts, whatever the doubts you have. So this will be a first problem. So in this problem, what we are given as per Cramp's open chain model, the preferred conformation of A leading to the major product during the Li-AlH4 reduction. So they have given a structure A, and we need to identify which will be the which of the conformation which gives the a major product, right? So which conformation will give the major product in this one? So that we need to find out. So first, we'll draw the structure in the Newman projection formula, right? So if you draw the structure, you can see. So in the Newman projection, so the front carbon will look like this, right? So first, we'll draw the carbonyl. So the carbonyl will be carbonyl, and here will be a CH3, this methyl, right? And on the back side, there will be a CH3 hydrogen, and there is one pH, right? So in the back side, there will be CH3H and the pH. So these are the groups are on back side, and LiLH4 reduction, it gives by LiLH4 gives the H minus, right? Hydride anion, which attacks on either from the direction of this methyl, from this direction, or by this direction. But which one is the correct one, that we need to identify, because if you see here, if the hydride minus attack through a B path, so from the B path there will be a steric repulsion because of steric hindrance due to this bulky methyl group. But if you compare this hydrogen on the left side, so the by path A, so this one path is the preferred one, because from if the attack takes place from this path, then the conformation, then the uh, steric hindrance due to the hydrogen is less as compared to this bulky methyl group. And and also while drawing, we have kept this highest bulky group on the side, opposite side, that of the carbonyl group. So this we need to keep in mind. So definitely what this a major product will be, if you draw a major product, then in major product, this OH will be carbonyl carbon, this OH double C double bond converted into OH, right? And hydride, which this one is a attack hydride that is came from the LiAlH4, right? So this hydride is here, and remaining backside groups are methyl group will be like this, hydrogen will be like this, and the pH will be like this. So this one is the major product. So which conformation here we can see this conformation you need to match. So we will check one by one. In the see here, in all other conformation, here pH is in these two, the pH is opposite to the carbonyl group. So these two approaches is correct one, right? See here, pH is opposite to the carbonyl group, but and here methyl group. So these two are obviously the incorrect one. So you need to compare in this one. And if you see here, the methyl group is on the right hand side, but here they have written on the left hand side. So this one will be a correct one. So the correct answer will be the A. So the A is the correct option, right? So so the option is the A. We'll take a next question. In the next question, what they have given, formation of major diastereomer in the following nucleophilic addition of methyl lithium, right? CH3 minus Li plus. This is the polarization of this methyl lithium. Involve the attack of nucleophile from Re or C phase, denote the phase around the carbonyl, while R and S related to the stereogenic centers. So in this structure, we need to first convert this structure into the Newman projection formula, and then we need to perform a nucleophilic addition reaction of this methyl lithium. So first, this structure, this structure can be represented by in the Newman projection like the here. In this one, carbonyl will be, and here there will be a hydrogen because it's aldehyde group, right? So this is the front carbon atom. So this one is the front side, and the back side one, this entire group will be on back side. So the if you see the back side group, here will be a methyl, here will be a hydrogen, and the pH will be here. So this will be the structure in the Newman projection. And now we need to do a attack of CH3 minus on this compound. So while attack of CH3 minus, they attack the how many possibilities are there? One is the this possibility, attack takes place from this side, right? Or second is the attack takes from this side. So there are again two paths, path A and path B. So in the path A, in the path A, there will be attack takes place from the side of methyl, right? Attack takes place from side of methyl. So in this side, if you attack takes place from this side, there will be a steric hindrance due to this bulky methyl group. But if attack takes place from the path B, this side is side of the hydrogen, that time the steric repulsion is less as compared to the side of methyl, right? So this attack on from this side is preferred one. So the product will be, if you draw the product, so attack takes place from this side, and the product, the structure of the final product will be like this. So this will be a, it will be converted into hydroxy group. Uh, here will be a hydrogen, and this methyl, which is came from methyl lithium, right? And the backside carbon, backside will remain as it is. So this one will be a product structure. Now we need to identify attack takes place from which phase, rephase or psi phase, and the carbonyl while R and sterogen center, which center is getting created after this, right? So that we need to solve. So I will take the solve problem on this next page, or I will write here only. Here only we can write. I will take a black marker. So see phase. If you see this phase, this if the attack from A side, the phase will be 1, backside 1, 2, and hydrogen will be 3. 1, 2, 3. This one will be the psi phase, right? This one will be a psi phase. And from this side, since this one is upside, right? Upper one get first priority, backside one get second one, backside carbon atom get second priority, and hydrogen will be third priority. So this side will be a re phase. So uh, the attack will be on the re. So this attack will takes place, and the configuration of this final product. So for configuration, we need to draw this. We need to convert. We need to convert this structure into the uh, normal structure, so as then we can able to give the nomenclature, right? So I will write the structure in expanded form. So the first priority will be to the carbon atom, carbonyl carbon. Here is the pH. Second will be to this, and third will be to methyl. So the configuration for this one will be the R configuration, right? So the attack takes place from the rephase, and the configuration of this steering center is the R. So the correct option is the R, sorry, G R. So this A is the correct option. So A is the correct option, right? So the correct option is A. We'll take a next question. So the third question is the which of the following conformation is involved in the generation of major product as per Falkin-Ahn model? So what is the Falkin-Ahn model? In the Falkin-Ahn model, we need to take the bulky group perpendicular to the carbonyl, right? So in this one, if you draw the structure in the Newman projection formula, the Newman projection for this compound will be like this. So this will be a center. The front carbonyl carbon will be like this, and the backside these groups will be Cl will be here, hydrogen will be here, and CH2PH will be like this. So this is the structure of this compound. Now in the Falkin-Ahn model, we need to bring this chlorine perpendicular to the carbonyl carbon. So which is exactly similar to the we need to when turn this to perpendicular, so the chlorine will be here, and the remaining two groups will be chlorine CH2PH, and here will be hydrogen. So this one will be a structure of this conformation in the Falkin-Ahn model. And in this one, if the attack of this methyl group takes place from this side of hydrogen in this Falkin-Ahn model. So this is the product. So we just check. See here, they have taken this group, but the chlorine is the bulky group, so wrong. In this one also it's wrong. In these two, you need to compare. if chlorine here is perpendicular, here also perpendicular, but configuration should for this one should be remain same, right? So if we check the configuration of this, see attachment, we have converted this structure into model, right? So in this one, see attachment like chlorine here, chlorine CH2PH and then hydrogen, chlorine CH2PH hydrogen, chlorine hydrogen CH2PH, chlorine CH2H hydrogen. So this one is the correct option. So option B is the correct option in this one. So this one just simple question. In this one, just need to understand. We should know the what is Falkin model. In the Falkin model, what the bulky group should be the perpendicular to the carbonyl, right? This one. So bulky group should be a perpendicular. So that's what we have to mind, keep in mind. And also the while converting the any starting material into the model, at that time we should always check the configuration should be remain same. See here, it looks like a chlorine is perpendicular, but the configuration of this center is not same. Configuration of this chiral center is not same in this model, so that's why this one is the incorrect one and this one is the correct option. So we'll take the next question. The fourth question: the addition of nucleophile E via anti-parallel mode to the following enolate leads to. So they have given the enolate. Uh, yes, they have given the enolate, and we need to just draw the mechanism for this, right? For this electrophilic addition reaction. So this enolate, how it will attack? So we'll just draw a little big structure so as we can able to draw the reaction mechanism. In this one, the double bond will be, this bond will be like this. See, and here will be a, right. So this one is the enolate. So while the reaction, with the progress of reaction, this enolate like this, the attack will take place to the electrophile, right? So this is how the attack will take place, and the remaining group will be there. Like here there will be a methyl group, here methyl group, here hydrogen, here also hydrogen. So this electrophile will come from opposite side, and the product after this, it cannot, when it converted into the product will look like this will convert into a boat form and a ketones, right? So this carbon convert into keto form, and the E, this electrophile will be here, and the remaining groups are the same. Here hydrogen, hydrogen, and remaining here also the same hydrogen, hydrogen. This remaining group are unaffected. Only the electrophile will attack from will be on the axial to this alpha of this carbonyl, right? So here will be the electrophile. So the correct option will be the B, because they have anti-periplanar mode. So anti-periplanar mode attack means the will go here and electron will come from outside. So this is called the anti-periplanar attack. So this INOLIT converted by the attack of this, when INOLIT attack on the electrophile, the product will be the B. Option B is the correct option in this one. So these are the some simple question uh, based on the INOLIT and as well as the by using the concept of INOLIT and the stereochemistry. So we'll take a next question. So next question they have given the burst reduction reaction of 4 third butyl cyclohexanone involves an intermediate base represented by. So burst reduction, what is the condition of the burst reduction? Firstly, burst reduction liquid or lithium or sodium in liquid ammonia. So after with this reaction, the this metal, let's say sodium gives one electron. So this electron attack on the what they have given cyclohexanone. So the structure of the cyclohexanone will be so they have given 4 butyl cyclohexanone, right? Either it alpha or beta doesn't matter, but only right. So here, sorry, 4 butyl cyclohexanone involve an intermediate with base represented by. So the by the reaction of Birch reduction, what will happen? This cyclohexanone converted into the here O negative and here one radical, right? So this we have to show. So how it will be, and this OH is O minus can then abstract the proton OH here one radical and like this. So now in this radical form, so we need to show uh, this radical is present in which form, like uh, here like option A, B, or C, or D. In all the options, you can see they have shown a radical in different positions. There, like here they have given one. It's on axial. Here in the in between the axial and equatorial, and here they have given the radical on equatorial. See in this one. So this is obviously the incorrect option, okay, because when it form O negative, then it will abstract the proton, so it will get then converted into the OH. So we can neglect this option D. Now remain the option are the AC, ABC. So in the ABC here we can see uh, they have shown here radical in between these. It is either not either axial or equatorial. So this one is also incorrect one. We can now we can compare only between the A and B. So in the A and the B, the option A is the correct one because when the radical is on the axial, so due to Foucault effect, probably you should you are aware about the this effect, right? Uh, in this one, I will add one slide. This radical, which is at this this carbon, which has the axial overlap with the C3 and C2. Where is C3? C3 and C2 here, and the C5 and C6. C5 and C6. So these two carbon have carbon, and these two carbon, it has a sigma orbital, right? So it has an axial overlap. So this is the reason this radical gets stabilization, which is not possible in this one when the radical is in the equatorial position. Here you can see in the ring. See, when the radical is on axial position, right here, when the radical is here and anti-log will be here, right? Coil bond will be here. So this bond and then this bond, it has a sigma orbital, right? So they, so so this sigma of this C2, C3 and C5, C6 will help to stabilize this radical. And if the radical is on equatorial one, then this overlap is not feasible, because when it is in equatorial position, so it is too away from the this one. So that's why this one is the stable one and stable radical, stable intermediate. Similarly, the next question is also here. Which transition state is more stabilized by CC bond? So in this one, you can see this one is the next question. In this one, they have given transition states, 4 transition states, and just they have asked more stabilized by CC bond conjugation, stabilized by addition CC bond. So in this one, here we can see in this one, here they have given cyano, COET, methyl, and this one. Here the hydride minus, which is cis to this methyl. Here trans. In this one, this is the example of Cplex model. So in this one, this hydride, which help, which is attacking hydride, right, to this center. So it has an overlap. This nucleophilic hydride anion, according to Cplex model in the transition state, attack by the nucleophilic hydride, this nucleophilic hydride anion to the carbon-carbon sigma star orbital of the carbon hydrogen nucleophile partially bond can be stabilized by the lateral overlap with the sigma orbital of adjacent carbon bond. So adjacent carbon, if you see here, the adjacent carbon bond, here we can see this anti-bonding orbital is stabilized by this adjacent carbon bond in this one. And in this one, this is the stabilizing factor, stabilizing bond, right? Similarly, here also, if you see here in this one, the stabilized by this carbon bond, and here will be the same. But here say electron withdrawing group are there, so it obviously this carbon carbon bond will be electron deficient, so here will be not that much better stabilization. But if you compare here in these two examples, there is electron donating group like methyl, and but the problem is here methyl is on the opposite side, it's not in the favor. So in the C model you can see it is in favor, right? So this electron uh, donating group of methyl will definitely help to stabilize this carbon-carbon bond, increase the electron density of this bond. So this enhance the stabilization in the C. So the C is the correct option. In such model, always keep in mind when there is electron withdrawing groups, which obviously destabilize or not that much stabilize, help to stabilize uh, this type of sigma carbon-carbon bond overlap. So, and the donating obviously increase the electron density, so help to stabilize this orbital. Similarly, it's exactly same question here also. In this one, this carbon-carbon bond help in the previous question. This bond uh, sorry, this carbon-carbon bond overlap will help to stabilize this radical. In the similarly one, these bonds have the significant effect. So this is how this is why uh, because of this methyl groups, this one is the more stabilized. Mention state. Here explanation you can read here also. See here they have given this stabilization, right? Here also there is stabilization, but there is no that much because if here electron donating group is present here the same side, then it will be good. But here there is no such donating group, only hydrogen. In the upper two options there are electron withdrawing groups which destabilizes. In the next question, alcohol which undergo fastest oxidation with CrO3. Cr double bond O, CrO3 they have again, and the alcohols given. So we should first we need to convert these alcohols into the uh, board form, right? Sorry, chair form. In this one, these alcohols will be all are trans, so no need to worry. So here methyl will be upside, hydrogen will be downside, right? And the carbon carbon 1 2. In the B, hydrogen will be and D option will be C. So these four options they have given, and which alcohol undergo fastest oxidation with the CrO3, right? So in this one, all are trans-decaying systems, and they are conformational result system, right? Trans-decaying, they are conformational result systems. So when the oxidation takes place, the oxidation in this system, see here methyl and hydrogen, here will be a repulsion. So in this one, if the oxidation takes place, this carbon get converted into this OH group converted into the carbonyl one. Similarly here also in the other. So what will be the transition states for all this one? So if you see this, these are the hydrogen in C and D option. So obviously uh, here we have seen hydroxy group. This hydrogen had not that effect on this the activity of this hydroxy group. Here it is on the equatorial side, and in the in this one also uh, it is on equatorial side. So in equatorial and axial, so the axial hydrolyze, sorry, axial hydroxy group oxidize faster because if you see the mechanism of this one, why this undergo oxidation faster, because if you see the transition state in this one, the transition state for this one will be the CrO3 O chelate with the Cr, and the attack of the hydroxy H2O takes place. Here is the hydrogen H2 abstract this proton, then this group convert here and like this. So this molecule finally get converted into the. So in this one, this repulsion helps to, although there is repulsion present, but the transition state experience this what we can say. In this transition state, it exhibit a steric strain due to this methyl, the repulsion with methyl and these groups. So this fastly converted into the product one, and this one is the rate determining step. So this transition state fall into the product is the rate determining step, since it involve the abstract of this proton and removal of this OCR bond. So this one is the rate determining step, but since it has the steric repulsion in this step, in the transition state, so the unstable transition state, so it get converted into the product faster. So so the rate, if you see the rate of this reaction is faster, because this step is the rate determinant step, and we know the rate determinant step only has the effect on the rate of the overall reaction. So if you see the option is the alcohol which undergo fastest oxidation with the CrO3. So the correct option is the A. A is the correct option, because in this one A, in the transition state, it's a highly crowded transition state is getting formed, and that uh, very speedily or fastly converted into the product. That's why the oxidation of this A is faster. If you see the mechanism is shown here also. Here explanation also given. The transition state of this conformation experience a served steric strain due to the presence of axial methyl group. This axial methyl group make a strain, uh, steric strain. So the it converted into the product faster as compared to other decalin systems. The next question is, the major product obtained in the following reaction is. So they have given HF with this acid compound, right? So major product obtain the following reaction. We need to draw entire reaction mechanism. So in this one, what is the role of HF here? Can anybody tell me? I will pause recording. You can tell me what is the role of HF. Okay, see, this is the reaction mechanism for this one. Because if you see convert to this structure into the Newman production formula, this upper COH and CH2 this will be lie here on front side, right? And CH2PH will go back side. So three gauge butane interactions among the large group. So this transition step is less stable. If you see the second transition state, if you rotate the groups in this one, there are only two butane gauge. Here there are three butane gauge interactions. And here there are two butane gauge interactions. So this one, this transition step is a periodon. Then HF, what will do? The HF form a carbene here, right? Carbocation. Then this carbocation, this phenyl group attack on this carbocation to form a 1, 2, 3, 4, 5, 5-membered ring, and simultaneously a deprotonation, proton removal of the proton followed by aromatization. It converted into this product. So this one is the major product. And the stereochemistry, if you see here, it will be a downside, right? Because if you see compare other, this proton will be upside and this one will be downside. In this one, this CH2PH upside and hydrogen will be downside. So here will be a dot side hydrogen and here upside one hydrogen present. So this is how the reaction works. The this mechanism of this reaction. A 5-member ring is more preferred as compared to 6-member. So the 6-member product, that one is the minor one, and the 5-member product one the major product in this reaction. If you want to draw a reaction without considering the stereochemistry, I will write here. If you neglect the stereochemistry first, so CH2PH. One minute, I will just. Oh, it has it got stuck, I think. So here, let it. If you draw this one in terms of HF, what happened? This CO OH converted into C triple bond plus, and then this pH ring or this pH will attack on this one, but preferably this pH is attack on the carbonyl because the 5-member ring is more preferred. Because if you see 1, 2, 3, 4, and the alpha of this pH will attack here, right? So if you expand this phenyl ring, so it attacks through this carbon, orthocarbon of this phenyl ring. So the ring form will be a 5-member and then followed by, so this carbonyl carbon, here will be a pH and H, here it's a hydrogen and CH2PH, and the hydrogen. So this how this will be looks like this transition state, and this proton removal followed by aromatization. So this 5-member ring, CH2 PH, and here will be a pH. So if you know the actually reaction mechanism, first we should know the reaction mechanism, then we can compare the stereochemistry. So this one is the major product, right? So if you see the options, 5-membered one is the major product. Oh, sorry. So this 5-member ring will be a major product. So I think here something happened. I will just, yeah, sorry that slide was stopped working. So we got the option. The option B is the correct option, right? Right. So the next question is the rate of saponification of the following ester A and B, R1 and R2 respectively. The rate of saponification of the following esters A and B. So they have given two esters. So the first ester we will draw it in the chair form. This will be a double bond O, Me, right? And it will be, if you draw here up, and this will be a axial, means it will be a lower side. Since this bulky group, so we need to flip this one. So this one will be here, and the CO2Me will be right. So this one is the A, and B is, if you draw a B, so this one also, oh, so directly we'll draw directly in this format. Right, and here it will also axial. So right, so these are the two structures, and this one is the A, and this one is the B, right? So we need to answer the rate of saponification of reaction of the ester A and B are. So if you say the ester A, it's the equatorial ester, and ester B is the axial ester. And we know the hardness of axial ester is the faster, because uh, axial ester are hydrolyzed. Sorry, axial. This is the axial ester, right? So axial ester hydrolyzed slower. So the saponification of the axial ester is slower than that of the equatorial one, because first step involves the formation of tetrahedral intermediate, right? Uh, for if it converted into, I'll add new slide. So Here, if it is ester OH, right? After at the time of hydrolysis, what happened? This attack here, and it converted into this one, right? So this group converted into the tetrahedral intermediate. Like here will be OH, here will be O negative, and here is the OH. So this how this center converted into tetrahedral intermediate. And if the center is at axial position, there will be obviously a steric repulsion here if any group present. So group or hydrogen, there will be a steric repulsion between this hydrogen and this tetrahedral site. So this steric repulsion will be takes place in axial when the ester group is at axial position. So that's why the axial slowly hydrolyzed than the equatorial. So the correct in this one and more stable one. If you see and if you see the stability, so obviously uh, if you compare the stability of these two, then the first one is the more stable than the this one A, because in this two both are the equatorial one, both are at equatorial. In this one is at axial position, right? This one although equatorial, this one is equatorial equivalent. But if you see this one, the another next group here in the A conformation, it is at equatorial position, but in the B conformation, it is at equatorial axial position. So in this one option A is the correct option because preferred conformation is A, right? And more stable than the B, and the rate of saponification for this one, that is equatorial one, is more as compared to the axial one, this axial one. So the option A is the correct option in this one, right? Because here why the rate if one ask why the rate is slower for the hydrolysis of the axial one, because the intermediate involved is a tetrahedral intermediate, and again it for tetrahedral again it will take some space in space, right? So there will be a steric crowding between this axial hydrogen and this axial, this entire groups as well as this water molecule. In the next question, consider the following reaction and find out the correct statement. So they have given the reaction. So NaBH4, it will be release H minus. It will have attack from this side, or hydrogen have attack from upper side, right? So which is the correct option in this one? Where the attack will be take place majorly rephase. So this one is the, if you see 1, 2, 3. If the attack takes place from upper side, it will be a rephase, and attack takes place from lower side, it will be a psi phase. So these two are possibilities of attack. So the options they have given, the two faces of the carbonyl are enantiotopic. See, uh, here already one chiral center is present, right? And now this face should be a distereotopic. So the option what they have given, the two faces of carbon are anisotropic. This is wrong. The two faces of carbon are distereotopic, right? This is distereotopic. And hydride is preferably delivered from psi phase. Here, 1, 2, 3, hydride preferably attack on psi phase. If the attack takes place from psi phase, means the equatorial attack. So equatorial attack, not preferred in NaBH4, while the addition of NaBH4 one, right? Because this one is the smaller one, and the axial attack is more preferable in this one. So what they have given, hydride preferably attack from the side phase. This is the wrong one. The half part is correct one, and the next hydride and attack on the side phase. This is wrong. So we'll check next option. The two faces of the kernel are anisotropic, and the hydride is preferentially delivered from the side phase. Anisotropic they have given, so this one is also a wrong option. And the last option remain. The two faces of the kernel are diastereotopic, correct one. And hydride preferentially delivered from rephase. Rephase means the attack takes place from axially. This one is the correct option. So rephase attack is preferred in this one. So the correct option is D. Because if you see here, there are two chiral center already are present. So the faces will be obviously the diastereotopic faces, not anisotropic. So these two options are by default get neglected. And remaining, if you see the hydride minus ion, when hydride released from the by the NaBH4, it attack on the axial side. Axial attack preferable. So that's why the option D is the correct option. So that's all about the today's problems. These are all problems based on the week 7 topics which covered by professor. And so if you have any doubt, please ask. Otherwise, I will left meeting. So I will just pause the recording here, and if you have doubts, please ask.